Hey guys, welcome back. So today we're going to do something completely new, but it's going to be using all skills you already know. So it's really, really important that you write this down because what we're going to do is basically discover this theorem, but it's one of those weird theorems that you forget later on. You forget why it is what it is, and so you might want to refer to this. So right now, please hit pause. And please do this integral on your own, on your paper, nice and neat, okay? Because we're going to do more with it. So please hit pause and integrate this. Okay, so hopefully you remember that the integral of cosine is sine of t. And then we're going to evaluate that from pi over 2 to 3x. Go ahead and plug those in and subtract. So this is the sine of 3x, which we can't evaluate because it's an x, minus the sine of pi over 2. And the sine of pi over 2, unit circle, that's right here, and the sign there is 1. Okay, so hopefully you did that okay. So that's our answer so far, but now what I'm going to do is ask you to take the derivative of this. So the original problem now has a derivative out in front. Let's say that that's how the problem started. Well, that would mean we're doing the derivative of this answer now. Okay? So now let's do the derivative of this. Okay, well, the derivative of sine is cosine. 3x times the derivative of the inside would be 3. And the derivative of a constant, that's 0. So this is our answer. All right, so now let's go back. We're done with this problem, but now we're looking for a shortcut, which is going to lead to today's theorem, okay? So if the original problem has a derivative and an integral, which seems like they undo each other, right? You're integrating and deriving, they undo each other. Well, if they undo each other, then our answer should just be cosine. Well, was our answer just cosine? No, it's cosine of the upper bound, the 3x. So in place of that t, you put the 3x and times the derivative of 3x. Notice that that's the answer, okay? So in the future, when there's a derivative of an integral, think to yourself, they undo each other, sort of. It's real close, except you end up plugging this guy in for the t's, okay? And you have to multiply by the derivative of what you plugged in. Now, this rule only works if the bottom bound is a number, any number, and the top bound is something, a function in terms of x or whatever, okay? So this is the fundamental theorem of calculus. Let me go back through it and summarize it formally. Okay, if you're doing the derivative of an integral, they undo each other. If the bottom bound is a constant, and the reason is, what happened to that constant is it basically went to 0, okay? So the bottom bound has to be a constant, okay? They undo each other, replace the t with the upper bound, and don't forget to multiply by the derivative of that upper bound. So here's the fundamental theorem of calculus. This is actually the fundamental theorem of calculus part 2. It says, if you have some function, okay, defined to be an integral, and you're trying to do the derivative of it, see, that's derivative, then it's the derivative of that integral. They undo each other. You just get what's sitting here, but notice the t changes to an x, and that's because you replaced it with this upper bound, as long as a represents a number, and the dx means times the derivative of x. Okay, here it is written again a little bit more directly. Okay, the bottom bound has to be a number. The a has to be a number. The upper bound you're going to replace with the t, and you have to multiply by the derivative of what you plugged in. That's the fundamental theorem of calculus, part 2. Part 1, by the way, is when you do the derivative of an integral with a definite integral with bounds, and you plug them in and subtract. We do that all the time, whenever we evaluate an integral. That's the fundamental theorem of calculus, part 1, and this is part 2. So it's very, very easy, but you forget why you're able to do it. It seems a little funky. So that's why I wanted you to make sure you took good notes of doing it the long way, and now we're going to use the shortcut. All right, so we have the derivative of an integral. We have to check the bounds. The bottom bound is a number, check. So just replace the t here with the 3x squared, and don't forget to multiply by the derivative of that. So our answer would be all in one step, no work. You don't have to integrate and then do the derivative, okay? So we get 1 over 1 plus whatever we were plugging in squaring, because it's had square right there. So this is a 3x squared times the derivative of that, which would be 6x. So I'll just put that on the top. Now be careful. When you simplify this, it's 3x squared times another 3x squared. Make sure you square both the 3 and the x squared. So your final answer would be 6x over 1 plus 9x to the 4th. That's it. It's very, very easy to do. You just have to know when to do it. So once again, you do this when you're doing the derivative of an integral. It seems like they undo each other, so the question is the answer. Almost. Okay, replace this variable with your upper bound, and don't forget to multiply by the derivative of what you plugged in. Okay, so give it another shot. Maybe hit pause and try this one on your own. Nothing too tricky. Same old, same old. Get the answer real quick. Okay, super easy. It should have been cosine of x squared times derivative of x squared, 2x. All right, how about this one though? Remember, the lower bound has to be a number, and this one is not. Do you remember how we fixed this? Okay, if we want to reverse the bounds, we can at any time, but in order to do that, you have to flip them and also add a negative out front. So this is the equivalent. Now you can do the problem the same way. So hit pause and do this one real quick in your notes. Okay, bring down the negative, replace all t's with 2x, and you're going to multiply by the derivative of 2x, which would be 2. I'll get that out of the way. And now I'm going to just replace my t's with the 2x. So it'll be 3 times 2x, which is 6x, sine of 2x. And then probably we'd multiply that together. Negative 12x, sine 2x. That's it. Okay? All right, now, the difficult problems in your homework today aren't going to be these. These are pretty easy, obviously. You can see we're doing them really quickly. The difficult ones are going to be the applications. So we're going to do all of the same applications, finding maximums and minimums, concave up, concave down. So every time you're doing these problems, let's say you're doing a concave up question. Well, that means second derivative. Well, the first derivative, you're going to end up doing this rule, okay? And you'll get this as your first derivative. And you can write that this is your first derivative, okay? Then you got to do the second derivative because you're doing a concavity question. So you just do the derivative of this, and you'll have to use your old derivative rules. This one would be a product rule. So here's an example of what I was talking about. You're still going to need all the stuff that you supposedly learned this year. So you might want to take out that justification sheet that I gave you, okay? This is asking for a maximum, and you don't even have to look at the problem yet. Just look at the words, okay? Maximum of something on a closed interval. Hopefully you are well trained enough to know immediately your approach. Maximum on a closed interval. Whatever it's the maximum of, you want to make sure its derivative is 0. You can add also changes to plus or minus, but since it's on a closed interval, you don't really have to do this because we have to do a t-chart when this is happening. So you're going to have an x, an f of x. Closed interval means check the endpoints and find any critical points with this. So hopefully you remember that that is your approach. Now, the t-chart for these problems is a good bit more work than you might think, okay? So let's continue. What I'd like you to do is go ahead and do that first derivative and set it equal to 0. Hit pause. Okay, I had to rewrite it. I knew I wouldn't have enough room. So the derivative is the fundamental theorem of calculus part 2, and it just changes that t to an x. Set that equal to 0. Never, but it's undefined when x is 1. So we would have derivative is undefined when x is 1. I should have written that in my justification, by the way. But 1 is not in the interval, so we don't even have to check it. So basically, we got nothing out of that, but now we need to do this. Well, f of x is defined to be an integral. So we're going to plug in that x right here. So this would be the integral from 2 to 2 of I don't even care, because when those numbers are the same, that's a 0. Okay? Now we're going to plug in the 5. That's the integral from 2 to 5 of this. Okay? Now, sometimes that's a calculator problem and you have to hit math 9. But we can integrate this. You may have forgotten what it is, but we need to get back on track. Okay? This is the entire denominator is to the first power Remember, the derivative of the natural log of x is 1 over x, and this is the one that in reverse you have a natural log. So this is the natural log of t minus 1, okay, evaluated from 2 to 5. So it's a natural log of 5 minus 1 minus the natural log of 2 minus 1. Sorry, that would be 1. Okay, the natural log of 1 is 0. Not that it really matters, because in the end, it wouldn't have even mattered if you fully simplified this. We know that this is a positive number. I don't know what it is, but it's a positive number, and this is 0. So the maximum occurs at 5. Now I have to reread the question. Do they want me to give the x coordinate or the y coordinate here? Find the global maximum. Typically, I think that means y coordinate. Often though on the AP exam though, they'd say value. Regardless, I give them both just to be safe. So the maximum occurs at 5, and the maximum value is the natural log of 4. Okay, you see how we basically incorporated everything we've already done. So that's why in this class, as long as you take all of your homework seriously, you don't get a chance to forget much, because it always comes back. Okay, the other things that you're going to need today, where you're going to basically apply today's rule to stuff you've already learned. Okay, you're going to need your rules for concave up, concave down, increasing, decreasing, all of that. One that you might have forgotten is also, I don't know what all this is. Hold on. Average value. I'm getting there. Okay, average rate of change. Okay, if they say average rate of change, don't forget what that means. That's your algebra 1 slope. So what's going to happen is, in order to find f of b, it's going to be an integral, and I think you'll have to use math 9. Okay, just be warned, you already know how to do that. Okay, when it says average rate of change, just by rote automatically do this, and then figure out where these things come from. So here's what your homework looks like. The one I'm talking about is number 11. You can see it's a calculator problem. Whenever you have a calculator problem, remember there are 2 things you need to know how to do on your calculator. You have to know how to find the integral with a definite integral with bounds on your calculator, math 9. But you also need to know how to do the derivative. That's n derive, math 8. You're going to need to know how to do both of those on your calculator. Derivative at a point and an integral with bounds on your calculator. These are all calculator questions. You can kind of tell by looking at them. All right, so number 11, average rate of change. Immediately, you should write on your paper, f of 3 minus f of 1 all over 3 minus 1. Then to find f of 3, that's f of 3 right here, which means this x is a 3. This goes in your calculator, math 9. Okay, that's a little hint. Now look at number 13. They want the second derivative. So when you do your first derivative, it's going to be the derivative of an integral. So they undo each other, and you just replace the t with an x, and you get the square root of tangent x. Next, they want us to find another derivative. So we're going to do the second derivative at point 2. Well, you don't need to do this derivative by hand because it's a calculator question. So you're doing the derivative of this at point 2. You should use your calculator to do that derivative. N derive, math 8. Okay? So you did the first derivative by hand, but the second derivative, since you're plugging in a point and you're going to need a calculator anyway, let the calculator do the work for you. Number 14, local linearization. What might that mean? Local linearization. This is a different book, so you might not recognize that term, but that just means equation of a tangent. So you need 2 things. You need point and you need slope. The point at 0 means you're going to plug in a 0 here, which means this is a 0. And since these numbers are the same, hopefully you can see that that's just going to be 2. The slope, however, means you're doing the derivative. Okay? Well, the derivative of that number out front, that 0, that goes away. And the derivative of this is the new rule. Replace the t with an x, and then plug in 0 to find that derivative. So you're just doing the equation of a tangent there. All right, good luck. Let me know if you need any videos working out the problems. Okay, guys? Hope you're doing well. I would, start with number 1 and number 10 and do your work out of order, because those are the 2 problems, number 1 and number 10. Those are the 2 where you just do the fundamental theorem of calculus without any applications. So do your work out of order. Do 1 and then 10 and then go back to number 2. Okay? Good luck all. Hope you're doing well.